Hello friends, we will be covering the following: pure AC resistive circuit, pure inductive circuit, pure capacitor, LCR circuit, inductance which is symbolized by Z, frequency change effect of inductance, resonance in AC, principle of tuning, graph of tuning, sharpness of tuning, frequency ranges, Q factors and its value. Before we study LCR series circuit, it is important to learn about three circuits. Starting from pure AC resistive circuit, we represent resistance by a basic circuit diagram. This is the first basic circuit diagram for resistance. Point 2. Here we know E will be equal to E naught sine omega 2 in case of pure AC resistive circuit. What will be the value of I? I will be I equals to I naught sine omega t. And how do we derive that? We derive in this equation we divide by R, left side and right side. Then we come to the value I is equal to I naught sine omega t. Resistance, the value for resistance will be V naught by I, or we can say E naught by I. It's the same thing as V equals to IR. So this is how we can write it down. Resistance, the value for resistance. There is no phase difference between current and EMF. So both in the phasor diagram you can see nobody is lagging behind or nobody is ahead. They both are in the same and there is no phase difference. Both red representing EMF and I representing blue line representing I in the same direction. I is small due to resistivity but have no phase difference. They are in the same direction. Pure inductor. We represent inductance by a basic circuit as this. This is the basic circuit for pure inductive circuit. Here again E equals to E naught sine omega t, or we can say V equals to V naught sine omega t. To calculate I, the second equation is to calculate I. Here I final value will be I equals to E naught L omega sine omega t minus pi by 2. So the difference between the V and I, the phase difference between V and I or EMF and I will be pi by 2. Okay, first let's derive this. How we have come to the value from V. We have derived this value all the way to I. How have we derived that? We know from the formula of inductance EMF is equal to L into di by dt. So we can say I equals to EMF dt by L. Integrating from 0 to pi 2, we get for sine omega t we get minus pi 2. So this is the value where current is lagging behind. So this is the value for E and this is the value for I. So V is ahead, V leads I by pi by 2. And this value is inductance reactance. So which is represented here, and this is XL is called the inductance reactance, the other symbol for resistance in case of inductive circuit. Here in this graph you can see I is lagging behind. The phase difference between E naught and I naught is pi by 2. E naught is sine omega t, which is shown in the normal graph that we have seen for EMF in the previous slide. This is the normal graph. As I is pi by 2 behind, therefore it lags behind by pi by 2 and it starts late in the graph. It's starting from this point. And again in the phasor diagram, we can see I is lagging behind E, which is by pi by 2. It is lagging behind by pi by 2. The third pure circuit that we will study is pure capacitor before we start with LCR circuit. Please look at the pure capacitor diagram here. This is the basic circuit diagram. Here you will note the same statement, the first, that is V equals to V naught sine omega t. To find out the value of I is equal to I naught sine omega t plus pi by 2. So here we have actually derived this value, how this has come ahead, and what will be the capacitive reactance. So we know Q equals to CV, or we can write down it, which is equal to CV naught sine omega t. I equals to dq by dt, taking the differential. So we will get, instead of writing sine omega t, we can write w cos omega t. Taking c v naught omega as constant as I naught, we derive this equation I equals to I naught cos omega t. So wherein we have find out that I naught is the value equal to c v naught omega. If we divide both this I naught and c v naught omega by v, if we divide both the sides, left and the right, from the left side, I by v naught can be written as r, and here c v naught by omega, when we divide it by v, so v from the numerator and denominator will get cancelled and we will be left with c omega. I by V is actually resistance R, and this C omega, we are representing it by XC, which is the capacitive reactance, and the value for capacitive reactance will be 1 by C omega. So this is R equals to XC equals to 1 by C omega, which is the capacitive reactance. In the graphical representation, I is ahead of E, and the phase difference is pi by 2. So if you see, I is ahead and the EMF E starts later. So look at the graphical representation. EMF graph is same, but I starts ahead. It is starting ahead. So if we look at the two I and E in the phasor diagram, in this phasor diagram, then E lags behind I by pi by 2. So here it lags behind by pi by 2. I is ahead of it in the pure capacitor. Now let us pull all the three LCR, that is inductance, capacitive, resistance, together in a circuit. So what we have done in this circuit, we have bring down all the three circuits that we have learned: the resistance, the capacitance, and the inductance, all three in one diagram. So what did we learn particularly in resistance? So we learned that they both are in the same line. Which all are in the same line? I and epsilon naught, or I say sometimes call it E. So they are in the same line. So here, if you see, they both are in the same line. If this is the line of the current, we are indicating this is the line for the current, then I and E are in the same direction. If pure inductance, E and I are pi by 2 as shown in this graph. So here it will be, this is I is lagging behind, and this is the potential here, which is EMF potential here written, and this is the I. So this is I is lagging behind. In case of capacitance, we can see that we are taking I only in one direction. So I is ahead and potential EMF is lagging behind. So here it is lagging behind. Okay. Now if for EMF, if we want to add all three up, we want to add 1, 2 and 3. So we want to add them up. So how can we do it? We are representing this for the resistance, we are representing this in form of here. So this is the Vm representing the EMF potential this line is representing the potential for resistivity. Similarly, VL is representing the EMF by the inductance. So this inductance is being represented here in this graphical line. This one is downwards. So this EMF, which is for the capacitor, is being represented in this line here. So when we have the three and we want to add them up, how can we add it? So first we will take VC and bring it upwards and minus VL minus VC. So we'll put a point here called as A. First subtract VL minus VC. We derive a new point, say A. Now we have to add this VM to VLs. Okay, to do that we draw a resultant from from this point O, say this is O to B. So here we draw a resultant here, which is up to this point. Okay, so we will draw a resultant here. Let us look at the close look at the horizontal line. It is resistance. XL minus XL is the difference between inductance reactance and capacitive reactance. So what is happening? This part is XL minus XC. That is inductance reactance minus the inductor capacitive reactance. Okay, and this is the resistance. Okay, and this resultant is denoted by a symbol Z. So Z is the resultant by Pythagoras theorem. So we will derive the value of Z now. I hope we will take only this graph forward. I hope this all is clear to you, how we have added it up. Now VR equals to, we are just keeping some values here. VR equals to IR, that you know, V equals to IR. So if it's for capacitance, we will say V equals to IX. See, and if it's for inductance, we will say L equals to IXL. So if it is V in total, then it will be V equals to IZ. So using Pythagoras theorem, we are trying to derive the value for Z here. So this square, which is the C square, should be equal to A square plus B square. Putting the value, R square will be here plus XL minus XLC whole square. This was Z square, so this will become under root. Okay, the value for this, which is cos phi will be equal to R by Z. Tan phi will be this value, which is XL minus XC by R. So XL minus XC by R. And when will I be maximum? When XL is equal to XC. Okay. Inductance reactance equal to capacitance reactance. So when will it be maximum? I will be maximum when reactance is equal to capacitance reactance. That is, in other words, the resistance of inductance is equal to resistance of capacitor. In LCR circuit, once we send an electron, it will oscillate. In an LCR circuit, once we send an electron, it will oscillate. The inductor will pull it ahead and sometimes backward. The natural frequency of this oscillation will be this value, which is 1 by 2 pi root LC. Minimum Z is called the natural frequency. So when the Z is minimum, it will be called as the natural frequency. As this frequency opposition is minimum. So it has the minimum opposition. So we will study about tuning, resonance, maximum current at minimum Z value is coming up in the coming up slide. So what will be the values for these? We will be studying all those further. Frequency change and its effect on inductance. Okay. Now we know that Z formula, Z, which is impedance, equals to R square plus XL minus XC, where XL is inductance reactance and the value for XL is L omega. XC stands for capacitive resistance and the value is 1 by C omega. Now what happens in case if the applied frequency is increased or decreased? We know if XL equals to XC, this is the time when it will have minimum resistance. But in case one value of XL is increased, then what will happen if we increase the value of frequency here? This was the original value of XL and this was the original value of XC, the both here, the frequency. Now if we increase one value of XL, say omega has been increased, and similarly because XC is 1 by C omega, so this value will automatically decrease. So the new values derived are this is for the new XL and this is for the new XC. But if we subtract XL minus the XC, the new value, anyway that value is going to be squared. So whatever the result comes out, that will be added to R. So which is the resistance. And this will increase, this will make anyway the Z value, which is the impedance, will increase anyway because it's in a square form here. Similarly, in case we have XL and XC and we increase the value of XC. What is XC? Capacitive resistance. If we increase that, the value for capacitive resistance is 1 by C omega. C omega is in the denominator. So we have decreased the frequency so that the XC value increases. Because XL, which stands for inductive reactance, here which is equal to L omega, it will automatically L omega, if the omega is decreased, so XL will decrease. So whatever the subtraction value XL minus XC, if that value XL minus XC is added to R, because it is square root, whatever value we get, it will be added to R. If the value is added to R, automatically resistance is more, Z is more, impedance is more. So this we have to note down the changes of frequency. It's not helping in this case. A series of LCR circuit is said to be in resonance condition when the current through it has its maximum value. So when is it in resonance? We will say when the current has the maximum value. The current, this is the graph, it has the maximum value. The current amplitude I for a series of LCR circuit is given by I is equal to V0 by Z. So here V0 by putting the value of Z, R square plus XL minus XC square. If XL equals to XC, then Z will be minimum. So this impedance will be minimum. In that case, the value of I will be maximum. So this graph here shows the variation of current amplitude with frequency in the LCR circuit. First curve with maximum current has the lowest resistance. Similarly, when the resistance is high, it flattens the peak in the graph and it's very low. See here. Mathematically, resonance frequency for point can be calculated as we know XL equals to L omega, XC equals to 1 by C omega. So L omega, if they both are equal, because we are saying XL equals to XC. So L omega equals to 1 by C omega. So the value of omega will be 1 by root LC. And the value for omega we can write down as 2 pi F for frequency equals to 1 by root L. So F can be written as 1 by 2 pi root 1 by LC. This is resonance frequency. Revising few of the terms that we have just discussed, Z is called impedance. Tuning and resonance are same thing. We have learned if applied force frequency is equal to natural frequency, then opposition is 0. That means less impedance. If less impedance, the current will increase. Principle of tuning and resonance. When natural frequency of a circuit is same as frequency of applied EMF, then this condition is known as resonance or tuning. In this condition, Z is minimum, therefore I is maximum. So I equals to EMF by Z, which is the impedance, resistance, equals to putting the value of Z here and putting the value of XL and XC. We derive at this formula. Please note down this formula as well. Variation of I with omega, that is maximum current by various frequencies. So we are having a circuit here, LCR circuit, and with different various frequencies. We observe with frequency omega. Okay, with this frequency omega, the current value is maximum. Then this will be resonance. We need to tune at this frequency to get maximum result. This tuning concept is same in radio receivers. That is, Z is minimum and I is maximum. So I is maximum and this is the W3 frequency level. So current has to be maximum. Under sharpness of resonance, we have talked about the amplitude of current. This maximum when it is maximum when Z impedance is minimum. With the help of various experiments, we have also observed that when power is half of peak, then we will not be able to hear disturbance. If the power is half, we are not able to hear the disturbance. When current amplitude is I equals to I root 2 times its maximum value. At this value, the power dissipated by the circuit becomes half. I naught is the current peak value. Similarly, P is power peak. This half value we have derived by experiments, various experiments. So we have come to know P1 will be equal to half the maximum power. Okay. So in under this, there will be, if the value is below 50%, there will be no disturbance. Putting it in the value, we know P is equal to I square R. So here it will become I1 square R equals to half I naught, which is the maximum, by I naught square R. I1 value will be equal to I root 2, which is equal to 0.7 I naught. So this is the relationship between the two here. So we get the relation between peak current and the current that will give least disturbance. This is the relation. Okay. So omega 1 plus change in omega, that is equal to omega 2, and here omega plus change in omega, that is omega 4. This value, the maximum, and this value will be our bandwidth. Okay. We will also learn about Q factors and sharpness of resonance. In a resonance circuit, which graph is better? Where sharpness is more or bandwidth is more? See, in this, the bandwidth is more. Here, the sharpness is more. If we see omega 2 minus omega 4 is less, this bandwidth is less. That is in this case. In case A, we notice sharpness is more. So what happens when the sharpness is more? Sharpness is more, there is less disturbance, less bandwidth, and less songs. In this case, more bandwidth appropriate for different songs. There might be disturbance, but it has larger bandwidth. Now, Q factor simply means how efficient a system is. Higher Q factor means low energy loss. There is less of energy loss. So Q stands for quality. So here in this graph, R1, R2 and R3. So these are here the resistance that you can see here. R3 and this is the P equals to, which is the maximum I naught square R. Here this is the 50% of the value, so it's written as this, which is equal to 0.7 I naught R square. Just repeating it down here, all these frequencies that are making power more than half are bandwidth frequencies. So these all are bandwidth frequencies here. We will use two expressions in this slide to explain Q factors. In our mobile, the electromagnetic wave voltage is very less. That is, say 0.02 volt. This is applied voltage. And that is the electromagnetic wave that is coming. It is only 0.02. But the voltage, or that is the voltage across R. The L, that is inductance present in the mobile LCR set LCR circuit, increases it by 600 and gives us the output as 628 volts. This voltage is across L. With this increased voltage, we can on our mobile set hear this electromagnetic wave comfortably. This ratio of voltage across L and voltage across R is called quality factor. So before we see mathematical expressions, let me explain the terms across. What happens is, if the voltage from here in this circuit of LCR, if the voltage is say 0.2 coming from here, so the voltage, if we take out two wires, one from this point and this point across R, if we take out the wire, the voltage here will be still 0.2. But as if we take out the voltage from across the L, the inductance from this point and this point, here the voltage will become 628 volt. As a result, we are able to hear it clearly. So every mobile has set of LCR circuit in it. And let's see the mathematical representation for it. So here I into L omega by R. Omega can be written as 2 pi f. F is the frequency. This frequency is at resonance. So if it says resonance, we can write L omega naught. So we can delete I from the numerator and denominator. We are left with L R, and we can write multiplied by 1 by root LC. Why? Because omega is equal to 1 by root LC. So we can further open this up by multiplying numerator and denominator by root L. So if we multiply by root L in numerator and denominator, we can write Q is equal to 1 by R divided by LC. This is one formula. Now Q factor is also measured of sharpness of LCR circuit. It is the ratio of operating frequency and the bandwidth at which poser is half the maximum power of current is 1 by root 2 times the maximum current value at resonance. Let me explain in simple terms. Say the operating frequency from Airtel tower is 400 and the bandwidth that we require is 600. Then the quality is not good. The quality factor is the ratio of operating frequency divided by the bandwidth in this value. Okay. Or let me explain one more time. Or other example is, we have a wireless mic of frequency say 100. The bandwidth is that we are paying for is say 400. We have an instrument, the mic frequency 100, and we are paying for 400. Here the quality factor will be good or bad. You tell me. The value will be operating frequency divided by the bandwidth. So 100 by 400. So these all questions can help you to decide if you want to buy this instrument or not. So quality factors. So these are the two methods of quality factors. I hope this was helpful to you. Thank you.